I'm happy to present my work. Before I explain my slide, since the topic today is about field enhancement, I will show you a video of one example to make plasma using a grape in your microwave oven. Yeah.
Grape?
Yeah, just regular, any grape. But I didn't do it by myself. I just watched the video.
밑에 5.
오케이. 됐다. 이거 어떻게 키우지?
어디였지?
너무 내려와서 너무
Yeah. Oops. 안 보이네. Let me try this one.
Welcome to Manual Madness's How It's Made. Today, we're going to learn how to make plasma. What is plasma? Well, you can look it up online. I'm going to show you how to make it. So, a few things here. We need
Can you see?
standard grapes. Then we need a cup. Glass. Please something that won't melt in the microwave. A knife and a microwave. So, what we do first is we're going to take the grape. We're going to chop the end off where the stem was. Not too much of it. Then we're going to fillet the grapes. I'm just going to go down. Now, the important part is make sure you don't cut it all the way. You want to have some skin connected. So you see, you can butterfly that. I'll show you from up top. Kind of butterfly the grape. So we're going to open up the microwave. If you have a round spinning table, make sure you put it down. You don't want the grape going everywhere. You want it to stay on the slab. And then we're going to take the grape. Wet side up. Just place it somewhere in the microwave. And then take your glass and fit it right over top. So, hope this works. What you're going to do, let me turn the lights off and off. What you're going to do is set your thing 15 seconds and start. Let's watch it.
You see? It's very dangerous. Your grape.
Not making that sound.
Yeah.
I stopped it at 4 seconds left because I actually thought the glass was going to shatter and it smells like something's burning.
So if you put just one regular grape in your oven, nothing happens. But if you cut it half and place in it, then there's high concentration in this small neck area, so that causes this plasma. And but the equation I explained today is a simple Laplace equation. I suppose the background potential is 1, and there are 2 inhomogeneities with conductivity K1. I assume it constant, K1 and K2. And the shape could be general. There are 2 extreme cases, as you know. The one is the insulating, where K is 0, and the electric field could not go to the normal direction. And the other one is the perfectly conducting case, where K is infinity and the potential U is constant on that case. And when K is not small or not too large, then the gradient of U is bounded. There are results for elliptic equation and also systems, and also for Lamé systems. I didn't write it here, but and the gradient blows up. Blows up means you keep the geometry of this inclusion D1 and D2, but let B1 and B2 and let the distance decay to 0. Then the gradient U blows up. It could be very of large magnitude. For dimension 2, the blow-up rate is 1 over square root epsilon, and in 3 dimensions is 1 over epsilon times log epsilon. There are many results. And let's see how it looks like the magnitude of gradient of U. So when you apply the background potential H, which is the entire harmonic function, whose magnitude of the magnitude of the applied field is 1, so the outside area is almost blue with magnitude 1. But in this small area, these two disks are not touching. Differently from the video I shown you, this case, when when the inclusions are touching, then there is no potential difference, so blow-up doesn't occur. So in this figure, there is tiny, small, different, 0.01. Then the gradient of U magnitude is like this. It's very bounded. It's bounded except this touching area, and this touching region, the gradient is as big as 1 over square root of the distance. That means 1 over 0.1. The one way I used in 2005 is to express the solution as the background applied field plus a single layer potentials on the two boundaries. Then the potential U satisfies the transmission condition on boundary D, one Dirichlet, one Neumann condition. And to make this U satisfy those boundary conditions, the density function Phi1 and Phi2 should satisfy this system of boundary integral equations. And lambda 1 is from the conductivity difference. K1 is from inside and 1 is from the outside. And since single layer potential is continuous across the interface, we only need to consider the normal flux condition. That's why there's this normal derivative. And one way we find the solution is take the formal expansion. Suppose you don't have this Phi2 term, then the Phi1 should be 1 over lambda times the right-hand side. That's why you have blue here. And in the second line, we do the same thing. Suppose there is only lambda to Phi2 and the right-hand side. Then Phi2 is 1 over this constant lambda times the right-hand side. And since you have this orange term, just plug into the first equation, then the Phi1 has a second term, and also do the same thing. Just put this blue term to the second line, then you have this second term. And so you do repeatedly this process, then the Phi1 and Phi2 are infinite series. And to to verify that this is actual solution, we should check the convergence and also the boundary integral equations. And this is yes to discuss. And actually, to discuss the single layer potential normal derivative is the same as the derivative of reflection with respect to the circle, the boundary of B. So P has this infinite series in terms of the reflections, and by repeating the reflections between two disks, at the end, all of the boundary point converge to the fixed point of this two combined reflections. And the distance between this two fixed point P1 and P2 is like square root epsilon. So you have the distance between B1 and B2, but this fixed point has the distance square root epsilon. So the gradient of U is like 1 over, when K1 and K2 are large, it's like the applied field H difference at those two fixed points divided by the distance. It's a mean value theorem. So when K1 and K2 are infinity, the gradient is like 1 over square root epsilon. And for the high conducting case, we have this term 1 over K1 and 1 over K2. And for case infinity, then the lambda is 1/2, and actually this operator for this density function P1 and P2 has the eigenvalue very small. So if we write the left-hand side as operator A and phi is two stack, one is P1 and P2, and say that's right-hand side H, and the operator has small eigenvalue. That means when you compute it numerically, that means discretize the boundary and then make a matrix equation. The matrix equation has also very small singular values, and that causes high condition number, so it's unstable. So that is bad news for computing. Computing in theoretically and also in numerically, but on the other hand, when you have high enhancement of field, we say it's superfocusing of electromagnetic field or light, then we can use it in displays. High field enhancement induce more emission of source electrons, and also use it to imaging some small microstructure, such as using the surface plasmons wave, and also it can be used to make a solar panel. And when you have a sunlight and make it to be enhanced in the structure of the panel, and that make you more solar panels. So there are many applications using the superfocusing effect. So what I want to do is to overcome this difficulty in the computing of the field when there are high enhancement effect, and then use it to these applications. I will not talk about applications anymore. Actually, I will explain to have the to express the blow-up behavior theoretically and use it to compute numerically. So let me write down the equation for the perfect conducting case, where K is infinity. Then the condition on boundary B is now constant, and then the flux on B1 and B2 are 0. And again, H is the assigned entire function. And as I said, if there are potential difference on these two conductors, then just a simple mean-value property tells you that the gradient U is bigger than, at least bigger than, or equal to the potential difference divided by the distance. So knowing the C1 minus C2 tells you the lower bound for the gradient. So what happens if there is no difference in the potential? I mean, C1 and C2 are the same, then no blow-up occurs. There are results for the spheres and systems, and also we have, in that case, gradient U decay exponentially near the touching point. Now the thing is to get this potential difference C1 and minus C2, and Mikyoung Lim gave a nice idea to use this function H, which is almost the same, except same to the equation of U, except that the flux is either 1 or -1 on boundary Bj, and it decay at infinity. I mean, before U was applied field H, but now the applied field is 0. Then the potential difference U on B1, boundary B1 and B2 is this integral of applied field H and the normal derivative of a small h. So knowing H, we have the potential difference. So for example, when B1 and B2 are discus, then using the property of Apollonius circle, that means for a disk and up to point, one is outside and one is the reflected point of P, then all the point on the boundary B has a same ratio in the distance to the P and the reflected point P. And in this two discus case, P1 and P2 are reflected point to each other. So the ratio x to P1 and x to P2 is constant. These numbers are different, but anyway, they are constant on one inclusion and also the other inclusion boundary. So this gives you that the h is log of the x minus the one fixed point minus log to the x minus p2. So this h is a combination of fundamental solution and log. Since this ratio is constant, h has also constant value. So you can check easily that h is the one I defined here for 2D discus case. And we can go further. With this h and potential difference, then U has this decomposition. The blow-up term is constant CH epsilon times H plus the background potential and this remaining term. And all is bounded. Whether epsilon is large or small, all is bounded. And the CH epsilon is the potential difference of U divided by H. So this first term has all the potential difference, and the other terms are zero difference. So only the first term blows up, and the remaining terms are bounded. So now to have the blow-up term, we should obtain h of x. There is PDE, so it's good news, and the remaining part is to get h and then evaluate the potential difference and also compute the boundary integral to have the potential difference of u. To discuss cases is simple. We have h, and then here is UB1 minus UB2, and U as the constant coefficient times h and the regular term. And then this all of x is now easy to compute. The equation for the density function has a bad condition number, but this all of x, it has related with more large singular value. So computing all is more stable than computing u. Okay, there are also results for a general shaped case when D is C2 and it is almost same as two discus, then you has this decomposition whose blow-up term is independent of the distance epsilon. What about 3D case? In 2D case, the fundamental solution is log x, and log x minus p1 minus log x minus p2 is constant. But in 3D case, we do the similar thing, but this 1 over x minus p1 minus 1 over x minus p2 is not constant on spheres. Yeah. What we know is the ratio, x minus p1 over x minus p2 is constant, not this form. So instead, what we can do is start from a function which is constant on boundary b1, and then add more term to make it constant on b2, and then again add more term to make it to be constant. So repeatedly we add more terms, and then here is the formula for h. We have a series of point potential function, and this is quite complex. In using this formula, we can have the optimal bound, lower bound and upper bound for the gradient of u. And there's result to approximate the gradient of u, and I'm preparing a paper with my students to make better this results than the previous paper. And the problem I want to explain now is the case when these conductivities are K1 and K2 not infinity, and B1 and B2 are discus with the radius R1 and R2. So I want to do the similar thing to the infinity case where U was decomposed into constant times singular function plus regular function. The main tool I use is the bipolar coordinate system. So where the x and y are now expressed in the bipolar coordinates psi and theta. Here you have this alpha, and that number is the location of the fixed point. The left fixed point is minus alpha 0. The right fixed point P2 is alpha 0, and in the bipolar coordinates and the Cartesian coordinates are related with this equation. So x plus iy, this minus P1 over x plus iy minus P2 is exponential of xi plus I theta. And the good thing to use this bipolar coordinate is the xi coordinate is log x minus P1 minus log x minus P2. That was h function, small h, which was essential to, which was a singular term in the perfect conducting case. So I use this coordinate and the angular coordinate theta with the fixed point P1 and P2, and this solid line is the boundary of B1, and the second solid line here, Xi2, is the boundary of B2. On B1 and B2, Xi is constant. And it has the value in between my negative Xi1 and Xi2 outside the outside the conductors, and it has negative infinity and positive infinity at these two fixed points. And interesting is, when you do the reflection with respect to the boundaries, then the Xi the magnitude of Xi increase. So m times of combined reflection R1 and R2 means m times the Xi1 Xi plus Xi2 to the Xi1. So, and the same thing happens for boundary B2. The multiple reflection means multiple of Xi1 plus Xi2. So the formal expansion I explained that the first part to express the solution in terms of multiple reflections are now related with this multiple of Xi constant on B1 and B2. And here is a solution expansion of U in terms of bipolar coordinate. This is very well known, and it's in many textbook of physics, maybe physics textbook. Yeah, it's very well known formula of express Laplace solution to the Laplacian in terms of bipolar coordinate. Since the basis functions are e to the n times psi plus I theta, we have the solution basis, and then from the transmission condition, here comes the coefficient an and bn. So you might think that it's all the problem is done. We have solution expansion, yeah, and an and bn are explicitly given. So when I explained this problem to the previous president of KAIST, when I have interview, and I said I'm doing this problem, and he told me that this problem is done in 1980s. So many people thought that this problem is done because there is formula and then you can compute it. But the thing is, when the distance is very small, then psi 1 and psi 2 is small as well. It decays to 0. And then here you have exponential to some multiple of a small number. So when this small number is really, really small, the convergence of the summation is really bad. Yeah. So this formula, we know this formula, nice formula, but it's harder to tell the actual value of this summation when epsilon is small. So the difficulty of this problem is a slow convergence when the distance epsilon tends to 0. And there are many other approaches, such as multipolar expansion. Then that means the series expansion in terms of the distance from the center point. And to have the coefficient of this expansion and the summation, summate this Taylor series expansion, there is ideas such as the image method, and approximate the coefficient by integrals of continuous function. This is the main point here. The summation is the formula itself is perfect, but to have to understand the behavior, we should approximate it to something we know better, and that is the integral of continuous function in this case. So for example, in the 3D case, the asymptotic for the gradient U I obtained using this idea. So the main works in this problem is to change the summation to an integral. And so do I have more time or?
More than 5 minutes.
Okay, so just 5 minutes or it's over?
More than 5 minutes.
Left?
No.
No, over. Okay, so I will stop. Sorry, because of the video. Yeah, so I did some results too in that idea to approximate the summation into integral, and I'll just give you the figure. Yeah, so it gives the level line of the magnitude of gradient U outside, also inside. Yeah, I'm working on the 3D case and lamech systems at this moment. Thank you.